Hello all. We will discuss in this lecture the transient in capacitor networks, the charging and discharging phases. First, we will begin by the charging phase. The voltage across the capacitor after connecting it to a circuit with a resistance for charging will be zero at the beginning, and as time increases, the current will flow. There is a rapid increase in the voltage of the capacitor at the beginning, and at this instant, the switch is closed. Electrons are drawn from the top plate and deposited on the bottom plate. We have the battery, positive and negative, connected to the capacitor through a resistance. The electrons are taken from the upper plate, and it will be positive charged by positive ions, and they are accumulated on the uh, lower plate. This process begins rapidly at the beginning, then the rate of increase in the voltage will be small until we reach the capacitor voltage will be equal to the supply voltage. The transfer of electrons is very rapid at first, slowing down as the potential across the plates approaches the applied voltage. Y as Vc will be equal to E times 1 minus e power negative t over Rc. When the voltage across the capacitor equals to the applied voltage, the transfer of electrons ceases, or the transfer of electrons will stop, and the plates have a net charge equal to the capacitance of the capacitor times the voltage of the capacitor, which is equal to E, then it will be C times E. This period of time during which charging is being deposited on the plates is called the transient period, or the time where the change occurs in the voltage of the capacitor. The quantity tau, which is the time constant, is defined as R times C. The tau is the time constant of the network, has the unit of time, and as shown below, R is voltage divided by current, and C equals the charge divided by voltage. The current equals the charge divided by time. Then we cancel charge with Q, charge with the charge, and voltage with voltage. 1 over T equals T, which is the unit of time. We have Vc equals, in the charging phase, E times 1 minus e power negative t over Rc, where Rc equals the tau, which is the equation for y equals 1 minus e power negative x. And for the discharging phase, as we will see later, Vc equals E times e power negative t over Rc, which is an exponential function, y equals e power negative x. The charging current for the charging mode or the charging phase. The exponential function can be used to plot the current. We have the current at the beginning as the capacitor is short circuit, then the current will be E over R, and the current, the flowing current jump to this value quickly, limited by the applied voltage of the circuit and the circuit resistance, which is equal E over R. Then the rate of deposit of charges decreases quite rapidly as the current reaches 0.368 or 36.8% of the maximum current E over R after one time constant only, until the current reaches to zero after 5 time constants, and the current will be approximately equal to zero. The equation for the current IC equals E over R times E power negative t over tau in amperes. The current of a capacitor DC network is essentially zero after 5 time constant of a charging phase. At 5 tau, the current is almost equal to zero. The equation of the current IC equals E over R times E power negative T over tau in amperes, we can recognize that during the charging, the major change in voltage and current occurs during the first time constant of the charging phase have paused, or we can say that the first time constant has the most or the largest change in the voltage or current for the charging phase. For I C equals V negative VC plus E divided by R, or IC equals E over R times E power negative T over tau. We substitute these two equations, E over R times E power negative T over tau by E minus VC over R. We cancel R with R. Then we have the VC equals E times 1 minus E power negative T over tau. The voltage across a capacitor cannot change instantaneously or change rapidly at the same instant. The capacitor's voltage for the charging phase, we have Vc equals E times 1 minus exponential negative t over tau. We have E power negative t over tau. At t equals 0, E power 0 equals 1. Then the capacitor voltage will be equal to 0, as we see here. And for E over negative t over tau, at t equals infinity, E power negative infinity equals 0, we have the voltage of the capacitor will be equal to E after about 5 tau, which is equal to 99.3%, which is approximately the supply voltage. The voltage across a capacitor is equal to the applied voltage after 5-time constant of the charging phase has paused, or the transient or charging phase of capacitor has ended after 5-time constant. We see that the time for a complete charging of capacitor will be equal to 5-time constants of the charging circuit, which is 5R times C. The capacitor can be replaced by an open circuit equivalent once the charging phase has paused, as the voltage of the capacitor will be equal to the voltage of the battery, then no current will flow in the circuit, so the capacitor can be replaced by an open circuit across its terminals. And for the characteristics of this capacitor at closing the switch, it will be replaced or substituted with a short circuit equivalent at the instant the switch is closed in an uncharged series RC circuit for the Vc equals 0 at the beginning of a charging phase, and as the charges are accumulated on the negative plate and positive ions on the positive plate, the voltage across the capacitor increases until it reaches the voltage of the battery. The resistor and the capacitor in series, the current through the resistor and the capacitor are the same, then we can get the voltage across the resistor by multiplying the current across the resistance, which is the current across the capacitor, by the resistance of the resistor using Ohm's law, which is equal to I R times R, where I C equals E over R e power negative exponential e power negative t over tau times R, then R is cancelled with R. We have E times exponential e power negative t over tau in voltage. The voltage across the resistor at the beginning will be equal to E, as the capacitor is replaced by a short circuit, and as the capacitor voltage increases, it reaches E, so the resistance will have a voltage of 0 after 5-time constant, or approximately 0.0067 of the value of E. Why does the voltage across the resistor start at a level of E? Because the voltage across the capacitor at the beginning is 0, and using Kirchhoff voltage law, we get that the voltage of the supply will be equal to the voltage across the resistance. When the capacitor has reached the applied voltage, the voltage across the resistor must drop to 0 at the same instant, as all the voltage of the battery will be accumulated on the capacitor terminals. Here we see the first example. We need to find the mathematical expression for the transient behavior for VC and IC and VR if the switch is closed at time equals 0. Plot the waveform VC versus the time constant of the network. Then plot the waveform of VC versus time. The required number 4, plot the waveform of IC and VR versus time constant of the network. For the fifth required, what is the value of the VC at time equals to 20 milliseconds. For the next required, on practical basis, how much time must pass before we can assume that the charging phase has passed. The next required, when the charging phase has passed, how much charge is settling on the plates of the capacitor. And the last required, if the capacitor has a leakage resistance of 10,000, I'm sorry, mega ohm, what is the initial leakage current once the capacitor is separated from the circuit, and how long will it take to totally discharge, assuming a linear unchanging discharge rate? First of all, we need to get expressions for VC, IC, and VR. For time equals 0, the switch is closed. Then we will get first tau, which is equal to R times C. R is 8 kilo ohm, 8 times 10 power 3, and C equals 4 micro, 4 times 10 power negative 6. We have 4 times 8 equals 32 millisecond. Then we get the resulting equation for the VC, which is E, the voltage of the battery, times 1 minus exponential negative t over tau. We substitute by E equal 40 and tau 32 milliseconds. We get the voltage across the capacitor. For the current is equal to E over R exponential E power negative t over tau. We substitute by E 40 volt and R 8 kilo ohm, and the tau equals 32 millisecond. 40 volt divided by 8 kilo ohm will be 5 milliampere times exponential E power negative t over tau, which is 32 milliseconds. For the volt across the resistance, which is equal to E times exponential negative power negative t over tau. We substitute by E 40 volt and tau 32 millisecond. Second, we will plot the waveform of VC versus the time constant 1 tau, 2 tau, 3 tau. At 1 tau, we have reached to 25.28 volt, and for 2 tau, we have reached to 34.6 volt, and for 3 tau, we have reached to 38 volt, and for 4 tau, we have reached to 39.3 volt, and for 5 tau, almost we are about the voltage of the battery, which is 39.7 voltage. For the VC equals 40 volt times 1 minus exponential negative t over 32 milliseconds. We have to plot for the next required the voltage VC versus time. We substitute now by the time. 1 tau is 32 millisecond, 2 tau 64 millisecond, and 3 tau is 96 millisecond. We will take a scale of 50, 0, 50, 100, 150 to 100 milliseconds. For the voltage VC, we can get the value of the voltages for each time we are having here, and we plot the waveform for the voltage across as a versus time in milliseconds for the equation of the VC we have obtained in the first required. Then we have to plot IC and VR. For IC is beginning at 5 milliampere at time equals 0, and as the time increases for 1 tau will be 1.84 milliampere, and for 2 tau 0.68 milliampere, and for 3 tau 0.25 milliamperes, and for 4 tau 0.09 milliamperes, and for 5 tau, which is almost zero current, 0.034 milliamperes. And for the voltage across the resistance is equal to E 40 volt E power negative t over 32 milliseconds. At the time equals 0, the voltage of the resistance equal 40, and as the charging phase began, we have a decrease in the voltage until we reach 0, almost 0 at 5 tau, or 0.27 volt at 5 tau. Now we need to obtain the voltage Vc at 20 milliseconds. We get the equation for Vc and substitute by t equal 20 milliseconds. Then we have the voltage Vc equals 40 times 0.465, which is equal to 18.6 volt. On practical basis, how much time must pass before we can assume that the charging phase transient time has passed? We have an assumption of a time of 5 tau for the completion of the charging phase. Then we have 5 tau, 5 time constants is the result, which is equal to 5 times 32 milliseconds, equal to 160 milliseconds or 0.16 seconds. For the at the end of the charging phase, how much a charge is sitting on the plate, or how much charges are present on each plate. We have Q equals C times V. The charge equals the capacitance times the voltage. Capacitance is equal to 4 microfarad, and the voltage across the capacitor is 40 volt. Then we have 160 microcoulombs settling on the plates of the capacitor. Now, if the capacitor has a leakage resistance of 10,000 mega ohm, what is the initial leakage current over the capacitor is once the capacitor is separated from the circuit, and how long will it take to totally discharge, assuming linear unchanging discharge rate? First, we need to get the leakage current using the leakage resistance. We divide the voltage across the capacitor by the leakage resistance, which is 10,000 mega ohm. We get the leakage current as 4 nano ampere. This 4 nano ampere will be equal to the charge divided by time, and the charge we have obtained from the previous required is 160 microcoulomb, and we have the current. We can divide the charge by the current to get the time. The time will be 40,000 seconds. We can divide by 60 to obtain the equivalent in minutes, and divide another time with 60 to get the equivalent in hours, which will be equal to 11.11 hours to discharge all the charges across the capacitor with a linear unchanging discharge rate. Uh, Now we will enter or begin the second phase, which is the discharge phase. For the discharge phase, we have increased another contact to as contact position to the circuit to uh, account for the discharging phase. If the switch is moved to switch to position 2, the capacitor will discharge. The resulting circuit in figure B will be the circuit used for the discharge phase. This is the circuit used for the discharge phase. We have the discharge. Initially, the current jumps to a relatively high value, and then it begins to drop. This value of the current can be obtained before it. We have to get the voltage across the capacitor is decreasing with time mathematically, beginning with E and ends with 0, which is equal to E times exponential e power negative t over tau. For this circuit, the time constant tau is the same as that of the charging phase. Tau equals R times C. When the current decreases, the current decreases with time. We have the similar formula for the current as the charging phase, but with a negative sign as the current has a changed direction. VR and VC are in parallel, so the equation for VR is equal to the VC but with a negative sign, accounting for the change of the polarity or the direction of the current, which is equal to negative E times exponential e power negative t over tau. We have the voltage across the capacitor equals E times exponential e power negative t over tau. IC equals negative E over R as the current. It changes its direction from the direction of the charging phase current equals negative E over R e exponential times exponential e power negative t over tau. For the V, R equals negative E times exponential power negative t over tau. The complete discharge will occur also after 5 time constant as the charging phase. And now if we move the switch between terminals 1 and 2 every 5 time constant, the waveform in figure will result for the VC and IC. Each curve, the current direction and voltage polarity are defined by the configuration in the circuits. For the charging as discharging, the current reverses direction during the discharge phase. For the voltage, it will charge to E, then discharge to 0, then charge to E, then discharge to 0. Each of these is having 5 time constants. For the VC of charging equals E times 1 minus exponential negative T over tau. And for the discharge phase, the VC equals E times exponential negative T over tau. For the current in the charging phase, it begins with E over R, which is equal E over R times exponential negative T over tau. And during the charging, the current decreases to 0 after 5 time constant. Then it will reverse its direction to be negative E over R at the beginning of the discharge phase, and then it decreases to 0 as the charges across the capacitor are returned to their initial positions. Then after that, and the current it will be negative E over R times E exponential E power negative T over tau, and then it will repeat the same pattern for charging and discharge. For VR, the charging phase equals E times exponential negative T over tau, and for the discharging phase, it will be negative E times exponential negative T over tau with a negative sign. Then we have the voltage across the resistance. At the beginning, it is equal to E. Then it will during the charging phase, the voltage across the capacitor will be equal to the voltage of the battery at the end. Then the voltage of the resistance will be 0 after 5 time constants, and after the the completion of a charging and the beginning of a discharging phase, it will reverse its direction to be negative E, and then it will discharge until it reaches 0, and then charging again, and so on and so forth. We have example number 2. Using the values of example 1, C equals 4 microfarad, C equals 8 kilo ohm, and E equals 40 volt. Plot the waveforms for VC, IC resulting for switching between contacts 1 and 2 every 5 time constants. For the discharge phase, we will draw the circuit for switch at position 2, and we will have the current reversed and the voltage across the resistance reversed. We can get tau, which is the same R times C, 8 kilo ohm times 4 microfarad equal to 32 milliseconds. And for VC equals E times E exponential negative T over tau, which is 40 times exponential negative T over 32 milliseconds. For the IC is equal negative E over R, E power exponential E power negative T over tau, which is equal negative 40 divided by 8 kilo ohm, which is negative 5 milliampere times exponential negative T over 32 milliseconds, which is the tau. For VR, we have VR will be equal to negative E times exponential negative T over tau, which is negative 40 times exponential negative T over 32 milliseconds. We have the charging phase equations. VC equals 40 times 1 minus exponential negative T over 32 milliseconds, and IC equals 5 milliampere. This is 5 milliampere, and this is 40 volt. 5 milliampere times exponential negative T over 32 milliseconds, and for VR 40 times exponential negative T over 32 milliseconds. And the equations we have obtained here for the discharging phase, we have the charging of the voltage of the capacitor from 0 to 40, then from 40 to 0, the 2 and 5 time constants, and then again from 0 to 40 and from 40 to 0 and so on and so forth. For the current of the capacitor, it will begin at the charging by 5 milliamperes if we substitute by time equals 0, e power 0 equal 1, and then it will decrease as the charging phase proceeds until it reaches 5 at 5 tau equal time. It will be a 0 current at the end of the charging phase, and for the discharging phase, it will begin by negative 5 milliampere and it will decrease until it reaches 0 as the charges across the capacitor plates return to their initial positions, and the cycle will repeat and so on and so forth. If the time constant equals 32 milliseconds, then it will charge in 5 time constant to 160 milliseconds, and this is charge in another 160, or total time of 320 milliseconds. And for the current, also will begin by 5 milliampere and reaches to 0 after 160 milliseconds, and then it reverses its direction to be negative 5 milliampere. Then it will discharge to reach 0 at another 160 milliseconds, or total of 320 milliseconds. If the time constant is equal to 8 milliseconds, then the charging phase will be in 40 milliseconds, which is 5 tau, and discharge in another 40 milliseconds, or total of 80 milliseconds. For the current, we have also the current will decrease from 5 milliampere to 0 in 40 milliseconds, then reverse its direction to negative 5 milliampere, and then it will discharge to 0 after another 5 time constants, or total of 10 time constants. We now see another example. Write the mathematical expression for the transient behavior for the voltage and current IC if the capacitor has initially uncharged and the switch thrown into position 1 at time equals 0. First, we have position number 1 for charging. Then find the mathematical expression for voltage VC and IC if the switch is moved, to position 2. Position 2 is a floating position at time equals 10 milliseconds. We have to check if this time is bigger than or smaller than the 5 time constants of the charging phase. Assume that the leakage resistance of the capacitor is infinite, as no leakage current will appear across the capacitor during being in the floating state. C. Find the mathematical expression for VC and IC if the switch is thrown to position 3 at t equals 20 milliseconds. Now we will plot the waveforms for the voltage and for the states of 1 and 2. I'm sorry, A and C, on the same axes using the defined polarities in the figure. Last but not least, we will see the charging phase. For the charging phase, the tau will be equal to R1 times C, 20 kilo ohm times 0.05 microfarad, which is equal to 1 milliseconds. We can obtain 5 taus equals 5 milliseconds to check for uh, uh, throwing the switch to the position 2 has the capacitor completed the charging or not. Also VC equals E times 1 minus exponential negative t over tau. Substitute by V or E, 12 volt, and time constant tau 1 milliseconds. For IC equals E over R1, 12 volt over 20 kilo ohm, which is equal to 0.6 milliampere times exponential negative t over 1 millisecond. For the switch thrown to position 2, position 2 is a storage phase, is a floating point at t equals 10 milliseconds. 10 milliseconds is equal to 10 tau, which is bigger than 5 tau. Then the charging phase has been completed. The capacitor is fully charged. Then the voltage across the capacitor will be equal to the voltage of the battery 12, and the current will be 0. the capacitor is fully charged at 5 milliseconds, which is equal to 5 tau, 5 of the time constant. Now we have in position C, or the third required, the third charging phase, using 20 milliseconds as the new time. As we have thrown the switch to position 3 at 20 milliseconds, where 20 milliseconds is the time equals to 20 milliseconds. The new time constant tau will be R1 times plus R2 times C, which is equal 20 kilo ohm plus 10 kilo ohm times 0.05 microfarad, which is equal to 1.5 milliseconds. And for 5 tau, we have 5 tau equals 7.5 milliseconds. We have 5 tau equals 7.5 milliseconds, which is equal to 5 times 1.6 milliseconds. For VC equals E times the exponential negative t over tau dash, which is equal to 12 volt times E exponential negative t over 1.5 milliseconds. For IC, which is equal to negative e over r times e power negative t over tau dash, negative e over the summation of r1 plus r2, which is equal to 12 divided by 20 kilo ohm plus 10 kilo ohm times exponential power negative t over 1.5 milliseconds. We have negative 0.4 milliampere times exponential negative t over 1.5 milliseconds. For the required number 4, we have to plot the voltage and current. For the voltage, it will increase from 0 to 12 in 5 milliseconds, and from 5 to 10 is having the same value. At 10 milliseconds, it will uh, be the same, as we have thrown the switch to position 2 at 10 milliseconds until we have reached 20. From 20 to 27.5, this is 27.5, and this is 20, then it will discharge to 0. Also for the current, we begin by 0.6 milliampere. It will reach 0 at the end of the charging phase and will be 0 from 0 to 10, and from 10 to 20 also 0. This is 20. Then it will reverse its direction to be negative 0.4 milliampere, and then it will discharge to 0 at 27.5, which is 5 tau at the beginning of 20 milliseconds. Example number 4. Find the mathematical expression for transient behavior of the voltage across the capacitor if the switch is thrown to position 1 at time equals 0. This is the charging phase. The required number 2. Find the mathematical expression for the transient behavior of the voltage across the capacitor if the switch is moved to position 2 at time equals 1 tau, which is incomplete charging. We have began the discharge phase at time equal 1 tau. Required number C, plot the resulting waveforms for VC and IC by parts A and B, and then repeat parts A to C for the current IC. First, we will begin the charging phase. We have a source conversion. We converted the current source and the resistance in parallel to a voltage source equal to the current of the current source 4 milliampere times the resistance 5 kilo ohm. We get 20 volt in parallel with the same resistance 5 kilo ohms. I'm sorry, in series with the same resistance 5 kilo ohms, which was parallel with the current source. And now we will close switch at position 1. We have the battery resistance and capacitor. We have tau equals R1 plus R3 times C. 5 plus 3 equals 8 times 10 microfarad equals 80 milliseconds. For VC equals E times 1 minus exponential negative t over tau. We substitute by E equal 20 and the tau 80 milliseconds. For the switch at position 2, the network appears as follows. The voltage at 1 tau can be found from the previous equation by substituting the voltage equal 0.632 times 20, or 1 minus e power negative 1, which is equal 0.632 times 20, 1 minus e power negative 1, which is equal to 0.362 I'm sorry, point 6. I'm sorry. I'm so sorry. I'm so sorry. Now we will have the voltage and current across the capacitor. For the charging phase, we can get the current IC, which is equal to uh, E over R1 plus R3. This is equal to E divided by R1 plus R3 times exponential T over tau, which is 20 over 8 kilo ohm times e power negative t over 80 milliseconds, which is 2.5 milliampere times e power negative t over 80 milliseconds. At time equals 80 milliseconds, the current ICU will be equal to e power negative 80 milliseconds divided by 80, or e power negative 1, which is equal to 0.368 times 2 milliampere, or equals 0.92 milliamperes. For the required number D, if the switch is moved to position 2, the voltage, which is equal to 12.64, we obtained it from 20 times 1 minus e power negative 1, which is equal to 0.632 times 0.632 times 20, which is equal to 12.64 volt. This is a voltage after 1 tau of the charging phase. This is a voltage across the resistance. This voltage will impress or pass a current equals E divided by the total resistance, which is 1 plus 3 equals 4 kilo ohm. Then the current at the beginning will be 3.16 milliampere. We have I at the beginning equals negative 3.16 milliampere times exponential negative t over the new tau, which is 10 microfarad times 4 kilo ohm, which is 40 milliseconds. And for the current, we have the current equal to 2.5 as a charging phase. It have decreased to 0.92, and after 1 tau, then it will reverse its direction to be negative 3.16 ampere, and it will begin the discharge phase for 5 time constants, which is equal to 5 times 40 equals 200. Then it will end at 280 milliseconds. We have added 200, which is 5 tau dash, to the beginning, which is 80 milliseconds. Find the capacitor voltage after the switch opens in the circuit shown in figure. What is the value of the capacitor voltage after 50 milliseconds the switch is open? This is left for you to exercise as a report. This is the end of this lecture. See you all in the next lecture.